Example number 5. We are going to determine whether the series from 1 to infinity of 1 over cubed root of n squared plus 1 converges or diverges using the limit comparison test. An equals the nth term, and then Bn. Let's see, can you figure out what this is going to be? Using the same strategies as the earlier unit, decreasing terms of insignificant value, 1 over n to the 2/3. Step 1. Identical to the direct comparison test. Step 2 is also identical to the direct comparison test. What does the sum from 1 to infinity of 1 over n to the 2/3 do? Does it converge or diverge? Hopefully you can see that it diverges as a p series, with p equals 2/3, which is, that doesn't look like a 2/3, does it? 2/3, which is less than 1. Okay, here's where the limit comparison test differs from the direct comparison test, and you know its logic already as we've discussed it in the earlier unit. The limit as n goes to infinity, we're going to take the ratio of the two, an over bn, and that's going to be the limit as n goes to infinity of, let's see, this is going to be n to the 2/3 over cubed root of n squared plus 1. Multiplying the reciprocal gives me that ratio. Now, let's take a look at this limit. This is the limit as n goes to infinity. I'll take the cubed root of n squared over n squared plus 1. And I'm just employing some fun properties of limits because I want to be technical here. It makes me feel better about myself. N squared over n squared plus 1. So that limit inside is going to equal 1. So it tells me that the limit of the an-bn ratio is equal to 1. Do you remember whether that's good or bad? It's good because it's bigger than 0 and it's not infinity. It's between 0 and infinity. That means we have conclusive results. In the limit comparison test, if your limit is between 0 and infinity, not including those endpoints, then the series will converge or diverge along with your choice of Bn. So we're going to say here, therefore, the series from 1 to infinity of an equals, being formal about it again, 1 over cubed root n squared plus 1 diverges also by the limit comparison test. Yay. Final example of the lesson. Example number 6. We want to prove whether this series converges or diverges. I believe that the hardest part about this is determining what Bn is going to equal. Here's my An. Then my Bn is going to be, well, I think of it as 8n is the higher degree term, and then let's see, n to the 7/2 is the largest term. So I'm thinking of Bn equaling 1 over n to the 5/2. N to the 1 minus n to the, or 1 minus 7/2. Step 1, standard an and bn are positive, continuous, and decreasing on 1, 2, 3, dot, dot, dot. Step 2, the sum of bn, which is the one we chose, 1 over n to the 5/2. What does that do? Converges as a p series. P equals 5/2, which is bigger than 1. Let's do the limit. Why don't you press pause and find the limit and make a conclusion and then reveal the answer. Answer revealed. The limit of the ratio an over bn equaled 8, which is between 0 and infinity, and therefore the sum of the infinite series converges by the limit comparison test. One of the key features was distributing this. The way I wrote it was times reciprocal, and then I distributed to get this expression, which led me to the limit of 8. Notice again in this particular lesson, and it will be true of the unit, we weren't concerned with what it's converging to, but whether or not this series was converging, period. Now there are some cases, like in the geometric, where we know what it converges to, but in a lot of cases we just know it converges, and we don't worry about what it converges to.